So transfer learning is a pretty interesting idea. Basically, you take something, because these networks can, on the best GPUs, the best hardware systems, it can literally take weeks for it to train and do a really good job. And some of these networks, I think something like ResNet 50 has, oh, I'm going to get this wrong, but literally millions of different parameters. It's 50, I think it's 50 layers long, ResNet 50. So like there's a lot of different layers of convolutional max pooling and different poolings layers, and over and over and over and over and over again. And you can just imagine that basically being like very, very complicated. And being able to build it from scratch and then train it yourself can, first of all, you have to build it from scratch, make sure it works, right? Or like the right architecture. That's one of the most important parts. But then also just having the time and the resources to actually train over long periods of time. So what's kind of cool though, is that we can actually do something called transfer learning, where if you have this architecture, you can essentially you can piggyback on top of that architecture and use it on your own data set. So for example, one thing you can do that was done is that you can take this, I can't remember what network it is, I'm not going to remember, but there's a group out of Stanford that took a network that was basically used to detect, like, you know, different animals, like image classification, like say, oh, is it a cow, is it a dog, is it a cat, you know, is it, you know, a bicycle, whatever. And they took this network and then they applied it to basically detecting whether cancer was malignant or not. And they actually were able to get a very good accuracy to that. It was due to transfer learning. And what's kind of cool is that they didn't have to develop their whole new system and then train for weeks and weeks and weeks on this new system just to detect like skin cancer. So what's kind of cool is that you can basically piggyback on top of this, and that's what they did, and ended up doing very, very well. And the reason why it really works really well is the structure of how convolutional networks really work, is that at the end right here, we have a classification. So remember that this basically will take a bunch of high-level features and feed it into a neural network and actually, you know, say, okay, from this high-level features, what is this image? So what's interesting though about higher up into these parts of the network, these are detecting very low-level features. So squiggles, patterns, splotches, those kind of things, and then it gets them more complicated features, more complicated features, more complicated, more higher level features at the very end here. But at the very beginning here, some of this stuff is very similar. For example, detecting whether something's a dog or a cat. You still need to know how to detect patterns, like basic patterns like outlines and stuff. The same thing you would need to probably detect for skin cancer. You would need to detect where the skin, like the different outlines and different colors and splotches and stuff. So these features are actually very similar for both use cases. So you can actually piggyback on top of this. And there's different ways you can do this. So the curriculum actually talks about these different structures and transfer learning. And this is transfer learning is pretty typical. But I wanted to talk about specifically about in what situations you would actually use, like how you would apply this transfer learning. So basically you can kind of split the different situations into 4 parts. Basically, if you have your own large data set, how similar is your data set? Okay, so is your data set very large? Is it relatively small? Is it similar to the original architecture or the similar training data that the architecture was trained on, or is it very different from each other? And depending on those situations, you can basically apply different strategies on this transfer learning. So I'm just gonna kind of go through some concepts of like when you would use, for example, a large data set. So you have a large amount of data and it's very similar data. So the main thing you're going to end up doing is basically changing out this fully connected layer every time, but it all depends about like what part of the convolutional layers actually matter. So for example, if you have a large data set with similar data, well, since it's similar data, these layers should detect low to high level features, all of this stuff right here. So what we're going to go ahead and do is we're going to reuse these guys again. So basically we have kind of like a head start. So even though it's not going to be the same data, it's going to be similar data, which means basically the weights are probably pretty close to where they should be. So we'll actually use this whole network again, and we'll just retrain on top of whatever the weights already were to begin with. Okay, and then what we'll do is we'll actually create a new fully connected layer. We'll randomize the weights and make sure this network makes sense to our specific data. So basically making sure it classifies at the end. If you had, like, for example, let's say this architecture was trained on like 1,000 different classifications, but you're only training on like 10 classifications, you'd want your neural network to represent that complexity of how many different classifications you'll have. And then you'll go ahead and put that new fully connected layer in here and retrain the whole thing, updating the weights, not just of your neural network, but also of the convolutional network. But because it's very similar, we can basically use the weights from from the previous architecture. That way it gets a head start since they're probably pretty close to what it should be already. Okay. So this one basically is like you get a new neural network and you retrain the whole thing, just starting from where it was before. Okay. Now, if you have a large data set, but it's different data, so imagine this, for example, is used to detect like animals, but then you wanted to use it to detect plants. Well, that's very different, you know, from each other. You might want to use some similar stuff, but maybe not. So one strategy you can basically do, this is like a general strategy, right? Of what you can actually end up doing is you basically have your layers to detect high to low level features. So you still want basically this architecture that does a really good job of detecting, you know, from low to high level features and detecting these parts. But what we're going to do is instead of just setting the weights and retraining it, we're going to randomize the weights all over again. So basically, we're retraining that whole convolutional network from scratch. We still have the same architecture, but we're just retraining the whole thing. So what we're going to do here is just go ahead and retrain all of those weights, and then of course we're going to put a new fully connected layer and retrain those parts. So basically, you pass through the whole thing back and forth, retraining all of the weights over. But the nice thing is that you don't have to change the architecture because you know it should work, and you have a large data set, so you don't have to worry so much about like, for example, like overfitting or stuff like that. Okay. So those are the two parts where if you have large data, if it's similar or different data. Basically, the only difference for similar data is that you keep these weights like, you keep the weight, you start with the weights that were already given since they're probably pretty close to where they should be. Okay. Then those comes like, you know, what if you have a small data set? So your data set's relatively small, maybe you only have like a few thousand images and stuff like that, but similar data. So for example, if you were detecting, you know, different types of plants, you know, and stuff like that, and you want to detect some new types of plants, but you only have a few images to actually detect on top of that. We can actually use this kind of strategy where what we'll do here is we'll go ahead and use that whole structure again, but this time, interesting, we'll actually do something called freezing these weights. And we'll basically hold these weights in place. So basically, you won't be able to update anything from the convolutional side of the network. So this part basically was like set in stone. You keep it frozen. You're like, all right, don't change this, but we'll change out this neural network at the end here and retrain. When we train it, we'll basically pass everything through here, okay, not change any of these weights, and then retrain on this network. So this way, basically, you are still basically getting those high-level features at the very end here based on the previous convolution architecture, and then go ahead and proceed with detecting it on the neural network itself. So that's kind of like, hopefully that kind of makes sense because we have a small data set. We want to avoid overfitting. We don't want to end up retraining this whole thing and specifically fit it for our small data set. We want to make it so it's a little more robust. And since this was probably trained over a large number of items, these features are probably already set in stone. You don't really need to train them over anyway. Okay. So far, this makes sense? Okay, cool. All right. And then our last one is probably like the most different, which is probably like a small data set, but different data. So this one's kind of interesting, I think, is that basically what you'll do here is that you'll remove these higher level features of the network. Okay, so basically you just want to use these parts for the lower level. Basically, since your data is very different from the original, they still have to use the first initial patterns, those initial like let's say like little squiggles and lines and stuff like that. But the higher level features, for example, like saying, oh, does it have whiskers? Well, we don't need that, for example, for a plant. But the problem is because your data is so small, we need to make sure we don't overfit. So we'll freeze the weights, but we'll actually cut off part of the network, the convolutional layers that were for the higher level parts, and basically only use these lower level features to create our features to feed into our neural network. And then of course we'll create a new neural network, and then we'll train the whole thing, basically updating the weight. I'm sorry, not train the whole thing. We'll train only the neural network, basically changing these weights, but these will be frozen in place since our data is so small. We don't want to accidentally introduce overfitting. Okay. So that's kind of like the overview of like how you would do transfer learning and basically the 4 different situations. And you can tell, like I say, large data, similar data, that's subjective, right? You have to kind of figure out exactly how similar, how much. I also say like about cutting off these pre-trained parts of the layers. You have to decide, you know, for your architecture, what makes sense to cut off. And this is where, for example, visualizing the data, visualizing what the convolutional layers are actually doing can be really helpful. Saying, well, okay, well, this layer here is doing a lot of detection on like whiskers and like other specific animal stuff, which is stuff I don't need. So I'm going to cut it off here versus all this stuff over here, a much more like lower level features like squiggles and like dots and such. Okay. So that's transfer learning. Any questions on that?
No, I think I'm good.
Okay, cool. And just to kind of show you an example, this is a project I had worked on. I did like American Sign Language image recognition. So I took images of, I don't know if I actually have it in here, but basically I took images of like different like hand shapes and stuff like that for letters. And I basically used different pre-training methods. And since my data was very dissimilar to, what's it called? From the original data, basically, of images. It was just handshake. I basically froze all of the networks, and my data was relatively small, pass it through, get something called the bottlenecks features, which are basically freezing on the weights of the convolutional layers, and then using my own network to train on top of that. So in that case, I actually got a pretty decent accuracy in that, considering that basically I didn't have to train my whole thing. This would, for example, like you can see all this stuff going on through, but this took like maybe at most like 3 hours compared to, you know, weeks and weeks and stuff going through. And you can see here the very what's the very high level, or the very light colored stuff means that it was accurate. So you can see there were some inaccuracies, but it was relatively good, hovering within 70-90%. But this is like, I was just showing like an application you can use, or that I used before. So just to kind of show you a little bit what this data would look like. Data pre-processing. So you can see, once I pull this up. Oh, I don't have it there. Okay, well, I'm trying to remember where I had that in the paper. Oh, it's probably in the paper. Okay, so I'm just kind of showing a little bit. So this, for example, the images, these are the images I was feeding it in, basically. And you can see here, it was using transfer learning, and my transfer learning stuff was much better than anything I built from scratch, which makes sense because the transfer learning stuff already had a pretty decent job of detecting different images, even if it was never trained on detecting hand shapes and stuff like that. So kind of a cool thing you can, again, an application that does work. It makes it a lot speedier and faster. Cool. All right, so that is transfer learning. That's the application. So our last one, I think is kind of a cool thing. I don't think the curriculum ever mentions it, but I think it's kind of a cool thing to do. It's called style transfer.